Hey y'all, it's your personal math teacher, Mr. Boyden. I'm back at it again today, and today we're going to make confidence intervals for means. Now, to understand this today, let's remember what we learned in the previous video about making a confidence interval for a proportion. I've got that formula right here on the screen. So, based on what we learned in the last lesson, what do we think it would look like for a mean? Well, it wouldn't be p hat, first of all. It would probably be x bar. And maybe we would think that it's still z star. That would seem intuitive. And then this right here, remember, that was the standard deviation of the sampling distribution for a proportion. So what would that be for a mean? Well, that would be this. Okay, so we would think that maybe this would be how we find a confidence interval for a mean. But don't write that down just yet, because there's a couple of problems with this. Okay, let's go look at them. Okay. Actually, the way we do it is like this. So yes, it's x bar. And notice the similarities. I mean, this looks very similar right here to the standard deviation for the sampling distribution of a mean. But notice it's not sigma on top, it's s sub x. And the other key difference to notice is that right there it's t star, not z star. Okay, what is t star? T star, it's still the critical value, just like how z star was the critical value. But it has n minus 1 degrees of freedom. Okay, probably want to write that down. That's going to be something we're going to be talking about more and more. Okay, it's something we'll need to know. Okay, and everything else about it works the way that you would think that it does. So what's going on? Why is that happening? What's up with that s sub x? And what's up with the t star? Okay, well, here's the reasons why those are there. Okay, first of all, we're going to use s sub x because remember, sigma is the standard deviation of the population. That's a parameter. And we can't know that just by doing sampling. Okay, so we don't know what it is. Instead, we're going to have to put what we do know, which is s sub x, which is for the sample. It's the standard deviation of the sample. So sample standard deviation. Okay, so that's going to mess with our standard error just a little bit. Now, what about a t-distribution? Because that messes with our standard error, we actually are going to have more variability now. And so we cannot use the normal curve anymore. We have to use what's called a t-distribution. And I want to show you what the t-distribution looks like, and I think you may understand why we use it then, and what the degrees of freedom are all about. So in this graphic here, we have in the middle what they're saying is a standard normal distribution. They're calling that a z-distribution here. It's kind of an old-timey way to refer to the normal distribution. I know it doesn't look quite exactly right, but take my word for it right now. Notice how these t-distributions, the ones in red and green, notice how they're similar and different than the normal distribution. Generally speaking, they're the same basic shape. Okay, so like even if you look at the one in red, the one in the middle right here, that one looks an awful lot like the normal distribution. Okay, and then if we get little tiny sample sizes, then it starts to spread way out. Versus if we have a larger sample size, there's less variability. This lines up with everything that we've learned about sampling distributions. Larger sample size, less variability, smaller standard deviation. Okay, so the key thing down here is, and I don't know if we really test you on this, but ideally it would be good to understand that a t-distribution is basically a normal distribution. It's just a little more spread out. But as the sample size gets really big, the t-distribution approaches the normal distribution. If you took calculus, it's the idea of a limit. As n approaches infinity, the t-distribution approaches the normal distribution. Now, one thing I didn't probably say enough of here is that it's important to know that the way we get the degrees of freedom is it's n minus 1. And so just to annotate that, that is the sample size minus 1. So if your sample size was 10, that'd be 10 minus 1. That's 9 degrees of freedom. And that's why that relates to this graph down here. If you have a small sample size, it's more spread out. All right, so 2 questions here. First one is find a t-value for a 95% confidence interval. But that's a trick question. It's not actually possible. And then we're going to try a second question, so we'll call them 1 and 2. The second question is, what if it was a 95% confidence interval when the sample size is 55? Okay, so for the first one, and we'll see this in the calculator in just a minute, I cannot do this because I have an unknown sample size. And that's very different than what we did when finding confidence intervals for P, for proportions. Okay, because there we didn't need to know the sample size necessarily to find the critical value. But here we do, because it's a t value now, and in order to know which t distribution we're looking at, we have to know the sample size. So we should be able to actually do number 2, a 95% confidence interval when the sample size is 95. Let's look in the calculator. In the calculator, it's going to work the same way as it did when we were finding z-star critical values for a proportion, except this time it's t. So we're going to go into our menu, where everything good happens, into statistics. And remember, before we went to distributions and then inverse normal. That was when we were finding a confidence interval for a proportion. But now we're going to come down, instead of inverse normal, notice right below that, our calculator is very nice to put that there for us. They have inverse t. So let's go to that. Okay, and notice this matches the exact information that was given in the question. So we need an area. It's a 95% confidence interval, so that's 0.025. If you're not sure why, I'm going to draw a picture in just a minute, and I'll make that more clear. And then if we're dealing with 55 as our sample size, remember the degrees of freedom is one fewer than that, so we're going to type in 54. Okay, and so that lands, oh my gosh, if I round that, that's 2.00. Okay, so let's go back over to the notebook for a second. So the t-star value for this is 2.00. Why is that? Because a t distribution looks something like this. And if we're looking for a 95% confidence interval, that means 2.5% of the area is on either side over here. Okay, and so that's why we're using 0.025, and our degrees of freedom was 55 minus 1. That's why we typed in 54 over there. Okay, so guys, logically that's the exact same thing as when we're dealing with a confidence interval for a proportion and finding z-star. We just have to remember that where we're going in the calculator now is t inverse, or inverse t. Now, let's talk about a little bit more about what degrees of freedom are and then the conditions that are necessary for this. Now, first of all, degrees of freedom. And you know what, y'all? I'm going to totally punt on this, okay? I'm going to just read to you what it says in my teacher edition textbook. It says, students are probably going to ask you to explain what degrees of freedom are all about. Unfortunately, there is no simple answer. For now, simply explain that the shape and variability of the t distribution depends on the degrees of freedom, which depends on the sample size. And what you really need to know is that the degrees of freedom is found with n minus 1. That's the sample size minus 1. Now, y'all, that's the stuff I kind of already explained. If if you need to know more about degrees of freedom, it's a little bit bigger topic than we have time for in here. But what you need to know, again, this is what you need to know and be able to use it for in this class. Okay, now what about conditions? I probably want to put these in bold because there's something that some students will forget. You got to have randomness. Obviously, everything in this class has had that, okay? This also has to meet the 10% condition in order to use a confidence interval for a mean. And then you also have to do something to establish normality of the sampling distribution. So one way of doing that was the central limit theorem. That's awesome. But if you can't use the central limit theorem, then we can do things like look at the graph of the sample and look for skewness or outliers. If we see skewness or outliers, then no, we don't get to proceed. Or if we're told in the question that a population is approximately normal, then we would know that the sampling distribution of the mean is also approximately normal. So that would be all good. And the reason I'm saying so much right there is because in the past I've had a lot of students say, oh, it's the central limit theorem condition. It's not. It's the normality of the sampling distribution condition. One way of meeting that condition is with the central limit theorem. So if your sample size is 30 or larger, awesome. Then don't even worry about it. Just say that and move on. If we don't have a sample size of 30 or larger, then we have to look more carefully. And we would hope that in a stats question, they would tell us that the population is approximately normally distributed. Okay, let's actually try a question. In the question it says use table B. We're not going to do that because we have calculators. Table B is from back in the days when you had to use tables of values to find t-star and things like that. So let's use our calculator. As always, I want to encourage you to pause the video and try it on your own. Let's see how you did. All right, use table B to find a critical value, t-star, that you would use for a confidence interval for a population mean M. They're calling the population mean M. That's interesting, not mu. Interesting. In each of the following settings. If possible, check your answer with technology. We're going to straight up find our answer with technology on these guys. Okay, so let's start with the first one. A 96% confidence interval based on a random sample of 22 observations. Okay, let's go straight to the calculator after we figure out what our tail areas are. Okay, and here's what I mean by that. First of all, I'm going to come over here on the right. I'm just going to draw a quick little distribution. Okay, it looks approximately normal because that's kind of what a t-distribution looks like. It's just a little more spread out. So if the central area is 96%, then these tail areas are 2% each. And then our sample was 22, so our degrees of freedom is going to be 21. So our inputs are 0.02 and 21. Let's go to the calculator. Menu, statistics, distributions, and we're going to do an inverse t. We said our area was 0.02, and our degrees of freedom were 21. Right, let's see what t star is. Okay, it looks like we're going to round that to 2.19. Now for this, what about the second one? Now they want a 99% confidence interval from a sample of 71 observations. So quickly we can see the degrees of freedom is 70. 99% confidence interval, if we have 99 in the center, that means we have a 0.5% on either tail, so 0.005 is what I'm going to use. Let's go back to the calculator. Let's do it as quickly as possible. Up, enter. And we're just going to edit this. So instead of 0.02, 0.005, and what was it? Was it 70? Yeah, okay, so 70 for our degrees of freedom. And we get 2.65, it looks like. Okay, what about number 2? Judy is interested in the reading level of a medical journal. She records the length of a random sample of 100 words. The histogram displays the distribution of word length for her sample. Determine if the conditions for constructing a confidence interval for the mean have been met in this context. All right, let's consider quickly what are the conditions. They are randomness. Did we meet that here? She records the length of a random sample. So that's good. Number 2 is the 10% condition. And so was her sample size less than 10% of the population? So a medical journal, she picked 100 words, so we're going to say yes, because 100 is less than 10% of all words in a medical journal. And then we need to establish normality of the sampling distribution. And do we have that? Well, we had a random sample of 100. So I'm going to say n equals 100. So CLT is satisfied. So what's the answer to the question? Determine if the conditions for constructing a confidence interval for the mean have been met. Yes, they have. We've met those. So yes, we would be allowed to proceed with constructing a confidence interval. Now, similarly, when we talked about proportions, we talked about finding the sample size to guarantee a certain margin of error. And so that's what I have on the screen now. I have that equation that we learned in the previous video. So if we were doing the same thing for means, it seems logical that we would do the exact same thing. Okay, so instead of z, now we know it's not z star, it's going to be t star. And we now learn that it's going to be not sigma, but it's going to be s sub x. But there's just a little bit of a problem. You are not going to know what n is because you're trying to figure out the sample size to get a desired margin of error. So you'll have to be able to find these other two. Now, what's going to happen when we go try to find t star? With t star, it's going to ask us for the area. That's totally fine, but it's going to ask us also for the degrees of freedom, which means we would have to know what the sample size is. And we obviously don't. That's the whole point of what we're trying to figure out, is what sample size we need. So we actually run into a dead end when we try to find a sample size for a given margin of error. Well, that's not good enough. We can't just say, I give up, too bad for me. And so what we do is we kind of have to fudge it a little bit, to be honest with you. So what we do, because we don't know the sample size and we don't know the standard deviation of the population, we're going to come in here and we are going to instead change that to z star. Okay, and so what I showed you up above, that was me just showing you the concept. what I'm showing you down here below now, that's actually how we find the sample size. We actually have to use Z. And the reason we can get away with that, well, it's honestly because we don't have a better way of doing it. So we're kind of just pulling a fast one and saying like, well, you know, a normal distribution and a t-distribution are kind of similar, so we're going to try to get away with it. Ultimately, guys, it's not an elegant solution, okay? But in statistics, sometimes we have to do this because we have no better way. And so that's what we have. Now, you may have noticed the other thing that changed is this changed into sigma. That is for the population, right? That's a parameter. So usually in an AP question, they'll give us some information like, in a study done in 2017, it was determined that the population standard deviation was blank, and then we get to use that number. No matter what, we're going to have an estimate for that. And usually we're going to find it, if we're actually a researcher, we're going to find it from someone else's study. Or if we are going to be doing an AP stats problem, usually they're going to give us a value to plug in there. Okay. So typically in AP, this is given. In the real world, it would be something we would do some research on. Okay, so this is what we use right here. It's not that thing I showed up above. So if you're someone who's taking notes right now as you prepare for an exam, please make sure this is the one that you have. This is the method that we're going to use. Let's try this question. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate the mean, mu, at the 90% confidence level with a margin of error of at most 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to meet the administrator's goals? As always, y'all, I want to encourage you to pause the video and give it a try. To figure this out, let's apply what we just learned. We just said that we're going to use Z star times the standard deviation over the square root of n needs to be less than or equal to the margin of error. And so let's use the values that we know. They want the margin of error to be at most 30 minutes, so we're going to plug in 30 for the margin of error. We don't know what the sample size is, so that's still going to be root n. What else do we know? Do we know sigma? They said a pilot study indicated that the standard deviation of time spent on homework is about 154 minutes. So that's the value we're going to use. That's what I'm talking about. Normally in an AP question, they're going to give us that value. And then we need to find Z star on our own. Now that's a 90% confidence level. Okay, so let's draw out a little normal distribution. If we have 0.9 in the middle, 90%, that means we have 5% left over for each tail. And so we can plug that into inverse norm. And we're going to get a Z star value when we do that of 1.645. Now guys, I did that before I made the video, so I know that's going quickly. If you want to pause the video and make sure you know how to find that, wouldn't be a bad idea. Okay, so that's the Z star value that we have. So 1.645. And y'all, that's our setup right there. Okay, so now we just need to work through the algebra on this. And away we go. The way I'm going to do this, I'm actually going to multiply up the square root of n, and I'm going to divide down the 30. So let me show you what I get when I do that. I get 1.645 multiplied by 154 over 30 equals the square root of n. And then we need to square both sides. The only thing I want to caution you on is when you square it, you got to square everything. So we need parentheses right there. Okay, and so then I'm going to have what my value of n is, although I seem to have magically made that an equal sign when it's an inequality. So now I know that n needs to be greater than or equal to, it looks like it says 71.3. Okay, so I'm going to say, since n needs to be greater than or equal to that, and we have to use a whole number of participants, I'm going to say we need at least 72 students. Okay, and that's a very typical example of how we find a sample size. Question 2. And guys, I don't necessarily recommend that you try this one without me. I'm going to show you a new technique in the calculator to hopefully make this question easier than it would otherwise be. Here it is. Biologists studying the healing of skin wounds measured the rate at which new cells closed a cut made in the skin of an anesthetized newt. Here are the data from a random sample of 18 newts measured in micrometers, just millionths of a meter, per hour. Okay, we have the data right there. They ask us to calculate and interpret a 95% confidence interval for the mean healing rate, mu. Now, before we do anything, we need to check the conditions for inference. Okay, so let's check our conditions. First of all, do we have randomness of the sampling? Do they tell us? Healing, random sample, they did tell us that. Random sample of 18 newts. Okay, let's go to our next condition. Our next condition is the 10% condition. So 10%, they measured 18 newts. We would probably say 18, what is the population? I guess it's just newts. Okay, so 18 is less than 10% of all newts. And what about normality? At first, normality is not looking very good on this one. Okay, because we say, well, the sample size is 18. They didn't say anything about whether or not the population is approximately normal. So we are going to need to look at a graph of the sample, okay, in order to get an idea about that. So we don't know yet, basically. So let's actually go get a graph of the sample. Let's switch over to the calculator and let it do this heavy lifting for us. You're going to need to add a new page, and that page is going to need to have lists and spreadsheets. As a rule, make sure you always name your columns. I'm just going to call it newts. And then I'm going to type in the data down here. So, poof, it's magic. Okay, all my data are there. Okay, let's visualize them. To do that, we need to add a new page. That's Control Doc. And we're going to add a data and statistics page. And let's look at our data. What we're looking for is skewness or outliers. Do we see any strong skewness or outliers? No. Okay, so there's nothing here telling us that it's not normal. Let's look at a different representation. Let's look at, see if we can get a histogram. Do I see any strong skewness or outliers? No, not really. And so this is where it gets weird, y'all. If we don't see strong skewness or outliers, then we're going to proceed with the calculation, okay? So, and when we did this, no strong skewness or outliers were observed. Okay, and so we're going to roll with it. And so now they want us to have a 95% confidence interval for the mean healing rate of mu. And so once again, we're going to let the calculator do the work. Let's go back to our calculator. And we're going to go back to the calculate screen, okay, where we did these initial calculations. And so now we're going to go menu, statistics, just as we did before in a previous video, confidence intervals. And we only have two kinds of t-intervals. We have a 2-sample t-interval and we have a t-interval. All right, so 2-sample or t-interval, we didn't do 2 samples. This is going to be a regular t-interval. And when we do this, they're going to ask us right away, hey, what's your input method? Are you going to use data or statistics? Well, we just spent all that effort typing in the data, so let's have that pay off for us right now. They want to know, okay, well, what list are we talking about? We're going to talk about the newts list. And 95% confidence level already filled. That's exactly what we wanted anyway. Let's click OK and see what happens. Okay, and so there is our confidence interval. So it looks like 21.5 to 29.8. And notice that in the background, it's calculating all the other aspects of that formula for us. It's noticing what the degrees of freedom is. They notice what the margin of error is. They calculated X bar for us, and then they actually gave us the interval. So let's go write that down. Okay, calculate and interpret a 95% confidence interval. So y'all, it's going to be that canned response. Let's write it out. We are 95% confident that the interval from 21.5 to 29.8 captures the true mean rate at which new cells close a cut made in the skin of an anesthetized newt. Y'all, I want you to compare your answer to mine. Okay, make sure yours is really specific. Notice I even referred to them as anesthetized newts because this study was not done on conscious newts. They're all anesthetized, which is for ethics probably a good thing. Okay, so make sure you are really specific and always include the context, and that's all you got to do. So we now know how to make a confidence interval for a mean and how to find sample sizes, and we even know how to do it in the calculator using data, not even finding the statistics ourselves. So I think that's enough for today. Hope this video was helpful, and I'll see you next time.